Hey everyone, welcome back to the channel. Today we're going to be diving into the world of complex numbers. Now don't let the name scare you. It's simpler than it sounds, and by the end of this video, you'll see why these numbers are so powerful and fascinating. Complex numbers have applications everywhere, from solving impossible equations to shaping technologies in engineering and physics. But first, let's start with the basics, so grab a notebook and let's unravel the magic behind complex numbers. So, what are complex numbers? Well, a complex number is a combination of a real part and an imaginary part. They are written in the form a plus bi, where a is the real part and bi is the imaginary part. The imaginary part comes from the square root of negative numbers. Now, in the past, this was something that people struggled with and could not do. So, for whatever reason, say you have a quadratic of x plus 1 equals 0. X squared plus 1 equals 0. So you'd use basic algebra and you get x squared equals negative 1. You take the square root of both sides to cancel the squared on the right hand side of the x. So you're left with x equals the square root of negative 1. Now, we all know that you cannot take the square root of a negative number. Well, that is not unless you use I, an imaginary number. So this is where the imaginary number came from, and it has its uses in many places of engineering, from electrical engineering to quantum mechanics. But here is a quick demonstration of what the letter I is used for. So you cannot take the square root of negative 1 unless you do this. I is an imaginary number that represents negative 1. Now keep that in mind because this is important. So now that we've established that I equals and represents the square root of negative 1, instead of writing the square root of negative 1, you can, with the basic surd rules, you can write the square root of 1 times the square root of negative 1. But we know now we have to find negative 1 as I. So what you can do is you can write it in this form. X equals square root of 1 I, which is just plus or minus 1 I. Right? So that's a basic representation of the imaginary number and a basic way that you can use it. So here's a few identities regarding to the letter I that you'll need to remember. And it's very important, so make sure you take notes and write this down. So I equals the square root of negative 1. I squared equals negative 1. Why? Because when you take the square root of the negative 1, it cancels out, so you're left with just negative 1. I cubed equals negative I, and I to the 4 just equals 1. Now, these are important to remember because when you're working with complex numbers, you take the square root of a negative number, and you can now do that with I. But when you want to get rid of I, you can manipulate the equation. Say it's a fraction, you can times it by the denominator if it's I, and you can do a lot of things with it to basically bring the I up to the power of 2, the power of 4, and eliminate I. So that's like a basic part that these very important identities of the imaginary number that you will need to remember. But to understand complex numbers, it's better to visualize them. So let's think of a graph where the x-axis represents real numbers. Instead of writing x, we are now going to write RE. That just stands for real numbers. And on the y-axis, we're not going to write y, we're going to write im for imaginary. So what the y-axis was now represents the imaginary numbers, and the x-axis represents our real numbers. This is called the complex plane. Now don't let the name scare you. These are a lot simpler than they sound. It is pretty much just like your basic Cartesian plane, but with a twist. For example, if we were to graph 3 plus 4i, feel free to give this a go and see if you get it right. But what the idea is we plot it as a point 3 units along the real axis and 4 units up on the imaginary axis. Simple. So to plot this simple complex equation, 3 is the real number part of the equation because you always have x plus y, and x is your first coordinate, y is your second, just like your basic x and y Cartesian plane. So 3 is your real number, so you're going to have 3, and 4i is your imaginary number. So your 4 is going to be up there, representing 4i. See, it's pretty easy, huh? Now these 2 points are going to connect up, like so. And this is how you plot on the basic complex plane. Now, obviously there are a lot more harder uses of this, but essentially the operations remain the same, and it's very similar to basic just algebra. You have to memorize the rules, and it will take a bit of time, but the more you practice, you will get the hang of these complex numbers and be able to do them with your eyes closed. Now, complex numbers can be added, subtracted, multiplied, and even divided. Let's go through a quick example of addition. So say we have the equation 2 plus 3i and 4 minus 2i. To add them, we combine the real parts and the imaginary parts separately. So just like your basic algebra. So what you're going to do, if you're adding these together, you can have 2 plus 3i, your first equation, plus 4 minus 2i. So using your basic algebra rules, you add like terms, and essentially that's it. That's all you have to remember. So you have your 2 and your 4 add up together to get 6, which is your real part, and your imaginary part, 3i minus 2i, just equals 1i, or I, right? And that's your basic addition of complex numbers. So all you have to know is when you're adding or subtracting complex numbers, you add and subtract like terms, do not do otherwise. This is the same as your algebra rules, right? Alright, so next, multiplication involves a little more work, but there's nothing we can't handle. Remember what I said at the start of the video, I squared equals -1. This is going to help simplify things. Alright, so let's give this a go. Keeping in mind I squared equals -1. So let's give this a go. 2 plus 3i times 1 plus 2i. Alright, I'm assuming that you have already learned algebra and you know the FOIL method or whatever method that you would like to use to expand these brackets. Doing complex numbers, I'd assume you already know how to do this, but I'll go through it. So to do the FOIL method on expanding brackets, you're going to take your first term. In this case, you're going to have 2 times 1. You're going to write that 2 times 2i is 4i. Then you move to your second term in the first bracket, 3i times 1 is just 3i. And then you're gonna take your second term and multiply it by your second term. So it's just a simple pattern. So 3i times 2i is going to be 6i squared. Now, this is why this is important, that you need to know your identities with imaginary numbers. Because if I squared equals -1, this isn't 6i squared, this is 6 times -1. This is what that represents. So what's 6 times -1? It's -6, right? So don't get caught out by that. And make sure you memorize the complex identities so you can do this stuff. Now, it's as simple as expanding the like terms, right? So what's 2 minus 6 minus 4? 4i and 3i add together to get 7i, right? See, it's not that hard. So why do complex numbers matter? Now this is a question that you might be wondering. Why do we even need complex numbers? Well, they're not just theoretical, but they're actually super practical. In engineering, complex numbers are used to analyze electrical circuits, and in physics they help describe wave functions. In math they unlock solutions to equations that would otherwise have no answers. Plus, they're essential for creating stunning visualizing patterns like fractals, and complex numbers are a key understanding and creating so much more. And just before I end the video, I'm just going to go over a few more quick examples of some complex equations and some practical ways that you would use these complex numbers. Alright, I want you to give this a go and see if you get it right. So let's do the equation x squared minus 2x plus 2 equals 0. Now please, I encourage you to pause the video and give this a go. Alright, so you have this quadratic. So what do you know about quadratics? If you know anything about the quadratic formula, you get -b plus or minus the square root of b squared minus 4 times ac all over 2 times a. And with your basic quadratic, your x squared, its coefficient is going to be a. The middle x term, its coefficient is going to be b, and c is just 2, right? The coefficient of x squared is just 1, because there's always a 1 in front of these variables, you just don't write them. It's like basic maths. Coefficient of b is going to be equal to -2 and c equals 2, right? Alright, so to solve this, just write it in the quadratic formula. If you don't know it, I encourage you to memorize it. This is very important, and once you memorize it, it's going to make your life a lot easier with these equations. So yeah, make sure you memorize that quadratic formula so you can be solving quadratics in that fast in the blink of an eye. But yeah, let's do it. So minus b, so that'll be minus 2, which is just going to evaluate to 2, but we'll leave the minus in there. Just so I can show you the entire process. B squared. Now b squared minus 2 is b, as we established earlier, 2 squared, minus 4 times a, which we said was 1, times c, which is 2, all over 2 times a. So that just becomes 2 plus or minus 4 minus 8, all over 2. Alright, if you've got this far, you're doing really good. So what do we do next? That is the $1 million question. So 2 plus or minus 4 take away 8 is -4 over 2. So I know, what do? You've ended up with a negative number inside of a square root. So if you try and put this into your calculator, it's gonna say that it can't do it. It's gonna give you an error, domain error, unless you've got some really fancy, expensive like graphing calculator that can do I. This is not gonna work. And during exam situations as well, remember that very often you can't use the more advanced calculators that can do these, so that's why it's so important that you learn how to do these yourself. So, remember what I equals the square root of negative 1. So we're going to write this equation in a different way. 2 plus or minus the square root of 4 to the square root of negative 1 divided by 2. Now the square root of negative 1 is I. So instead of writing the square root of negative 1, we are just going to put an I in there. And that's your answer. 2 plus or minus the square root of 4i divided by 2. Obviously we can simplify this down a bit more. You can factor out 2. So, we'll divide it by 2, as that before. Alright, so the 2's will cancel, and when you have something over 1, you don't bother writing the 1, it's just, divided by itself, it's just itself. So 1 plus or minus 2i is your answer. Alright guys? But yeah, if you left it in this form as well, you'd be fine. Alright. It's not that big a deal, but it is good to simplify things down, especially when you can. And during exams, you will pick up a few marks. Alright, so the last 3 topics I would like to talk about, and I think it's important that you should know this, is we're going to talk about Euler's form and Euler's form with complex numbers. Alright, so let's give this a go. So what is Cartesian form? Cartesian form is your basic, just complex number form that we've been using for this whole entire video. It's going to look like z equals 3 minus 2i, but we've just been writing it like that, but usually you denote it with the letter z. And that's just your basic Cartesian form. So like what I was talking about before, this is your real part, this is your imaginary part, because it has the I in there, right? So if you plot these on the Cartesian plane, what do you get in your real part? You get 3, in your imaginary part you get minus 2. So the points are going to line up, and boom, that's your complex number. See? Easy, right? But then there's another way of writing these, a few other ways that are extremely important to remember, and they do definitely have their uses, especially in engineering. And these questions are very likely to come up on your exams if you're doing any form of advanced maths like that in general. So yeah, let's go over these and make sure to take notes. Write down the equations and just make sure you can remember these without having to look back at your notes. So remember them off the top of your head, right? Because these are very important. Alright, so let's give this a go. This is going to be slightly harder than the stuff we've been doing before, but you can do it. So let's give this a go. Z equals 4 minus 4 root 3 I. Alright, so what do we do first? Let's identify our imaginary part and our real part. Alright, sweet. So, this is in Cartesian form, just like your normal y and x form. Like easy, right? Cartesian form. Sorry about my messy handwriting. So, now that you know this is in Cartesian form, what does polar form and Euler's form look like? So these are the basic formulas behind it. Polar's form is you have your modulus of z. Z equals your modulus of z. That is times by cosine of theta plus modulus of z times I times the sine of theta. Now you can factor out the z, write it like this: cosine theta plus I sine theta. That is polar form, right? Alright, now we need to talk about what exactly does the modulus of z look like? And theta, it's not your basic theta. Well, it is, but there's something you have to know because there's a certain domain that it can lie in that you definitely do need to write it in this correct way when you're writing about complex numbers in these forms. So what does this mean? Your modulus of z is essentially, imagine you have a triangle. This is going to be your hypotenuse, right? So now that that's your hypotenuse, that's what the modulus of z is. Say you have a real part of 2 and an imaginary part of 1, right? So your modulus of z, imagine you link these up. You know your height is 1 and your length is 2. It's just a basic triangle, that's all it is. So I'm sure you know Pythagoras would say, old mate Pythagoras would say, 2 squared plus 1 squared equal your hypotenuse. If you don't know that, pause the video, go search up Pythagoras and make sure you know about this before coming back to that. So now z is exactly the same. You take your two components of your imaginary and your real part, and for z, if you have z equals 4 minus 4 root 3i, the modulus of your hypotenuse is going to equal 4 squared plus minus 4 root 3. And that is your modulus of z. Let me quickly type this into the calculator. Unfortunately, that one is a bit tricky. So, 4 squared plus minus 4 root 3 all squared. And that is equal to 8. So that is so say I have a triangle, this is equal to 8, right? That's all that is saying. So now you've established your modulus of z. Now remember that the formula asks for theta as well. Now, to calculate theta, it's just going to be tan y over x, or because we're now in the complex plane, it's going to be, it's tan minus 1 of, that's going to be imaginary on real. That's all it is. That's how you find your angle theta. So that's going to equal arctan of, and this is your imaginary part, 4 root 3, minus 4 root 3, and your real part is just 4. So type that into your calculator. Make sure you are in radians, because when working with complex numbers, we are always using radians, not degrees, so make sure you're in radians. So arctan minus 4 root 3 all divided by 4. And that is going to equal minus pi on 3, right? And if you get this in decimal form or your calculator can't do exact trig ratios, you don't know exact trig values, doesn't really matter. Just make sure you round to a few decimal places so you don't lose many rounding errors or like that in your equation. But here's where the tricky part comes in. So pay attention. So we've got minus pi on 3. What was the original equation? Says 4. And then the imaginary part is 4 root 3. So from your unit circle, you know that tan is going to be negative in this quadrant, right? So this is negative pi on 3. Alright, so this angle stays exactly the same as it is, but what you need to know, I'm just going to explain this to you real quick. If you're given a complex number that plots to here or something, and the angle you get is just this angle here, in the complex plane, you always want the angle from 2 pi, which is your 360 degree point, just your start of the unit circle. You want the closest way it can get to the angle, either through here or through here. Which leads me onto your domain is going to be equal to pi minus pi. So if you're given this angle here, what you're going to do, you know this is pi here, right? And you want this angle. So it's just going to be theta minus pi is going to give this angle there. So yeah, I thought make sure you know that and you've memorized it, alright? Because that's very important in the complex world. But this one is lucky. This one's nice and simple. So you know your modulus. I'm just going to copy this real quick, just so you can see the equation. So we established the modulus of z equals 8 theta equals minus pi on 3 radians. Alright, so simple as you just write it into your formula. So it's going to be 8 cosine of minus pi on 3 plus I sine of minus pi over 3. Right? That is polar form. To prove this, you know, to find your x component or your real component, it's just going to be your modulus 8 minus times cos of minus pi on 3. Let's type that into the calculator. 8 cos minus pi divided by 3 equals 4. And that's good because that's what our equation started with. So you're literally just going between two different ways of writing the same thing. So feel free to try that in your calculator, and it's always a good check to do at the end to make sure that you have indeed done it right. Alright. So now that you know what polar form is, Euler's form says this: z equals modulus of z e I theta. Now it's as simple as substituting in these values, so I won't explain this too much, just copy it down and make sure you can remember this, alright? Especially if you're doing complex numbers. In uni, school, especially during exams, you need to remember this. So modulus of z we already know is 8 I, what was theta? Minus pi on 3. This is Euler's form for writing complex numbers. Alright. Alright, cool. Thank you so much for making it this far in the video. The last thing that I want to go over is solving roots of imaginary numbers. This may seem hard, but I can assure you once you get the hang of this, it's quite easy. It's very similar to, it actually is Euler's form, just in a different way. So I'm going to tell you the formula, and I want you to write this down and remember this. So you're going to have the form of modulus of z times e. You're going to have I outside of your bracket e, and this is going to be theta plus, this is going to be 2 times k times pi. and this is times 1 on n, and sorry, the modulus of z is also to the power of 1 on n. Alright, now I know this might seem very confusing, especially if you haven't seen this before, but before you freak out, just take a few deep breaths, and let's go over this, and you are going to get the hang of this in no time. So, let's start with the example, z to the power of 4 equals -1. What would you do to solve for the complex roots and find all real and imaginary solutions to this problem? Alright, so you've got this formula up here, and very similar to what we have before, n represents the power that z is to. So this is 4 equals n. Alright, k, this is important. You know 4 equals n. K is going to have, k is the number you substitute in that's going to give you different solutions, alright? So k is going to have a few different values, but the basic rule to remember, if n equals 4, k is going to be all the numbers that come before 4. So that is going to be 0, 1, 2, and you guessed it, 3. That is the numbers that you're going to use as k, and k is going to be your primary variable that is going to give you your imaginary and different real solutions to this problem. Alright, so now that is established, z to the 4 equals -1. So first up, find your modulus. Your modulus is same as what we were doing before. There's no imaginary number, just imagine there's a 0i, -1 squared plus 0 squared. I know obviously you don't have to write 0 in, it's very unnecessary, but just for the lack of a better term, I'm going to do it anyway, just to help you understand this topic as the best you can. Because generally we do not write 0i, it's just assumed that I is 0, alright? That's what it means. So the square root of -1 is just 1, alright? N equals 4, k equals 0, 1, 2, and 3. So these are all the values that k can equal, the numbers that are less than 4, but not less than 0. Alright, so now we know that, this simple matter of substituting it back into this formula. So make sure you write this down. So, modulus of z is just 1. To the power of 1 on n, we said is 4. E, I, theta, alright. Theta is going to be equal to, or in this case, what is this theta going to equal? Because you can't put 0 into your calculator. But from the unit circle, you know this is pi. So theta, therefore, equals pi. But guys, just also remember that it's not often you get a question like this, and you can usually just solve this by putting your usual arctan equations in your calculator like we have been doing before. But yeah, for this instance, theta equals pi, and it's a simple matter of substituting your values in, plus 2 times k times pi times 1 on n, which is 4. Alright, it's getting a bit messy, so I'm going to move this down here. Alright, so I'm going to do this once, and then for the rest of the times, just know you substitute k in. 1 to the power . So 1 to the power of 1/4 is just 1. So that's 1 ei. Now theta plus 2 times k we're going to substitute k as 0 first. So that's the first number k can be, so that's going to be pi times pi on 4, which is just pi on 4. And if you know your trig identities, you're going to know that is 45 degrees radians, alright? So that's your first solution. So your second solution, all you're going to do, you're going to substitute 1 where k goes. So you're going to have 1e I pi plus 2 pi times 1 on 4. Now what is pi plus 2? Pi plus 2 pi is going to be 3 pi times 1 on 4, which is going to be 3 pi on 4. So your next solution is 1ei 3 pi on 4. Alright guys. And also remember, if you don't know the exact trig value or you're a bit unsure, make sure to type this into your calculator, because it must lie in this domain or this domain. It cannot be greater than this. It cannot be greater than that. You always want your shortest path of action from your real axis as theta. So let's type 3 pi on 4. Let's see what we get. So that is equal to approximately 2.36 radians. So that's going to lie about here, 2.36. And this is perfectly okay, right? Because it's in the domain, but you need to do this for every solution. Make sure it is in the correct domain. Alright guys? Alright, so next it is just rinse and repeat with the different k values that we have. And the next k value we know is 2, so that's going to be ei pi plus 4 pi is going to be 5 pi, which is going to be 5 pi on 4. Alright guys. Now you don't have to write the 1, I'll do it anyway, just to make this easy to understand for everyone. So type 5 pi on 4 into your calculator, making sure you're in radians. And you see, look guys, 5 pi on 4 is 3.9 approximately radians. This is your angle right now. You cannot use this angle in the complex plane. So what do you do? From your unit circle knowledge, you know this is 2 pi. So you're going to do 5 pi on 4 minus 2 pi. You're going to get a negative value. And this is equal to minus 3 pi on 4. So that is your angle. It's equal to theta. Alright? Because it has to lie in the domain of pi to minus pi. So you get minus 3 pi divided by 4.
We're going to wet and wild in the morning anyway. Let's just go and wait.
Okay, cool.
If you're up for wet and wild in the morning,
Yeah, sure.
that'd be good.
Okay, bye. Alright, so now I've established this as our next solution, you're going to rinse and repeat again for this was k equals 2, your last solution of k equals 3, which is gonna get you 7 pi on 4. And remember to type this into your calculator. 7 pi divided by 4 is equal to 5.49 radians, which lies about, it's going to lie about there in your unit circle. So now, do exactly the same as you did last time. What you're going to do is 7 pi on 4 minus 2 pi. Essentially, you're subtracting everything else, which is going to leave you with this angle theta right there. And it's a negative value with your sign convention. Alright, it's going the other way. Alright. 7 pi on 4 minus 2 pi is just equal to minus pi on 4, which, if you know your trig identity, is minus 45 degrees. Alright, guys? Your last solution is going to be 1ei minus pi on 4. Alright, so let's write this all out. Your first solution, ei pi on 4 at k equals 0. Alright, so our next solution is ei 3 pi 4 at k equals 1. The next solution at k equals 2, ei at k equals 2, what do we get? Minus 3 pi on 4. So you notice a pattern, huh? This is at k equals 2, e at k equals 3, we just get minus pi on 4. Interesting, look at that. Can you pick up the pattern? It's very interesting from these polar forms, and when you actually plot these and solve the nth roots and all the complex roots of numbers, you get these interesting patterns, right? Alright, so now you've got your 4 values, let's go ahead and plot this just to show you a visual representation of what is actually going on. So you have e to pi on 4. To get the x component, it's just going to be 1 cos times pi divided by 4. Which is equal to root 2 on 2. Now you can leave these in decimal form, but if you want to use exact values, I think that's a bit better, but it's up to you. Either way it is correct. So next up, let's solve our y component. It's just going to be sine of pi divided by 4, 1 times sine is also root 2 on 2. Sorry, that's your I component, not y component. Next up, 3 on 4 is just going to be 1 cos 3 pi divided by 4 is going to equal x, and then 1 cos 3 pi on 4 will equal y. So feel free to type this out yourself. So you're going to have cos 1 times cos of 3 pi of 4 is going to equal, so your real part is going to equal minus root 2 on 2, and your imaginary part is going to be sine of that, which is just root 2 on 2, right? Alright, almost done, guys. So minus 3 pi on 4. What's our x component going to be on that? Just rinse and repeat, but you've picked up your patterns already. Same but negative, so negative root 2 on 2 for your real component. And your imaginary component is also minus root 2 on 2. Alright, let's do our last solution. So minus pi on 4 cos of minus pi on 4 is going to equal root 2 on 2, which is your real component, and sine of minus pi on 4 is going to equal your imaginary component, minus root 2 on 2. Alright, guys. Alright, so now we have got all our solutions from that problem. I'm going to plot this out just so you can see where they go and the fascinating shapes that these make. These are very predictable patterns, and right now we're very deep into mathematics, so I think it's pretty interesting what shapes and patterns these cause. So our first plot is root 2 on 2 and root 2 on 2 imaginary. Next plot, minus root 2 on 2, that's this one here, and root 2 on 2 again. So first plot, this is our second our second equation got us on the graph. Third one, minus root 2 on 2, which is here, minus root 2 on 2 in your imaginary, which is approximately here. Alright, guys, so let's plot that. Sorry, that's not great. Try and do that better. Get a point here. Alright, so our last point is positive root 2 on 2 and then negative root 2 on 2 for your y component, which is going to mean our last point is going to be there. Now, do you notice that makes a square? And what's also interesting is that the original equation was z to the power of 4 equals negative 1 to the power of 4. I'll let you think about that. But yeah, essentially that's it. With other different values, you get equilateral perfect triangles in different shapes. So it's very fascinating where this branch of maths will lead you. And it's very good for engineering, physics, all that kind of stuff. Very useful for electrical work as well. So yeah, guys, I hope you enjoyed the video. I know it was a long one, but thank you so much for watching. I hope you learned a thing or two during this video, and that now you can do a bit of complex numbers. And in future videos, I'll be making stuff on a different like kind of styles in math. So calculus, either basic algebra, trigonometry, the unit circle, vectors as well for those more advanced mathematics people. So yeah, if you have any requests, just leave it in the comment below. I would love to help you out. But thanks so much for watching, guys. I hope you enjoyed the video, and I'll see you next time. Bye.